How AI locks onto targets in under zero point 0.3 seconds. The physics of machine perception. Imagine opening your eyes and instantly recognizing a moving object, estimating its speed, predicting its direction, and deciding what it is all in less time than a human blink. That blink takes about 300 to 400 milliseconds. Modern artificial intelligence systems are now approaching that same time scale. In controlled environments, machine vision pipelines can identify, classify, and track objects in under zero point 0.3 seconds, not because they think faster, but because they operate on completely different physical principles than the human brain. This video isn't about weapons or tactics. It's about perception physics, how machines convert photons into decisions faster than biology ever could. Everything begins with light. When photons strike a camera sensor, they generate electrical signals inside millions of microscopic photodiodes. A modern CMOS sensor operating at 240 frames per second captures a full image every 4.16 milliseconds. Some industrial sensors go far beyond that, exceeding 1,000 frames per second, meaning a new visual snapshot every single millisecond. Each frame contains millions of pixels, and every pixel carries intensity and color data. That raw data enters a pipeline known as computer vision for processing. Before any AI understands anything, the image must be normalized. Brightness is corrected. Noise is filtered. Contrast is adjusted. Edge gradients are calculated. This entire stage happens in hardware accelerators and graphics processors in under 5 milliseconds. Already, we are far faster than biological vision. Human retinas send signals through optic nerves at roughly 10 meters per second. Neural interpretation in the visual cortex introduces another 80-120 milliseconds of delay before conscious recognition even begins. Machines skip biology entirely. They move straight into mathematics. Once preprocessed, the image enters a neural network. Modern perception systems rely on convolutional neural networks, or CNN. These are layered mathematical structures designed to detect spatial patterns. Early layers detect edges and corners. Mid layers detect shapes and textures. Deep layers identify complex features like vehicles, animals, or people. Each convolution layer performs millions of matrix multiplications in parallel. On a modern AI accelerator capable of 200 trillion operations per second, 200 TOPS of full object detection paths can complete in under 10 milliseconds. That means the system has already classified everything in the frame before you've consciously registered what you're seeing. But classification alone is not enough. AI systems must also understand motion. This is where temporal prediction enters. By comparing consecutive frames, optical flow algorithms measure pixel displacement. If an object moves 12 pixels between frames captured 5 milliseconds apart, the system calculates velocity using v equals delta x slash delta t. If delta x equals 12 pixels and delta t equals 0.005 seconds, that's 2,400 pixels per second. Converted into real-world units using camera calibration, the AI now knows actual speed. Kalman filters and Bayesian predictors then estimate future position. These mathematical models assume motion continuity and apply probability distributions to predict where the object will be next, often 50 to 200 milliseconds into the future. This predictive step is critical. It allows machines to compensate for processing latency by acting on where something will be, not where it was. Humans do this subconsciously when catching a ball. AI does it numerically. Now comes decision fusion. Multiple sensors contribute simultaneously. Visual cameras provide shape and color. Infrared sensors detect heat signatures. Radar measures distance and velocity using Doppler shifts. LiDAR builds 3D point clouds with millimeter accuracy. Each sensor operates on different physics. Radar uses radio waves traveling at the speed of light. Infrared measures thermal radiation in micrometer wavelengths. LiDAR fires laser pulses and measures nanosecond reflections. All this data converges inside a fusion engine. The fusion engine aligns timestamps, compensates for sensor offsets, and combines probability maps. This process uses tensor mathematics and runs continuously. Modern systems fuse inputs at rates exceeding 100 updates per second. That means every 10 milliseconds, the AI updates its world model. At this point, the system holds a continuously refreshed mathematical representation of its environment, but speed alone doesn't explain sub-0.3 second response. Parallelism does. Unlike the human brain, which processes perception largely sequentially, AI systems operate massively in parallel. Thousands of cores analyze different parts of the image at the same time. GPUs contain tens of thousands of arithmetic units. Specialized neural processors execute matrix operations with extreme efficiency. Instead of thinking step by step, machines think all at once. Now let's talk latency. From photon capture to classification typically looks like this. Sensor exposure, 2 ms. Image preprocessing, 3 ms. Neural inference, 8 ms. Motion estimation, 5 ms. Sensor fusion, 6 ms. Decision output, 5 ms. Total, approximately 29 milliseconds. That's under 0.03 seconds. Even with buffering and safety margins, full perception cycles routinely complete under 100 milliseconds, well below the 300 millisecond human reaction window. This is why AI appears instantaneous. But perception is only half the story. Prediction is the other half. Modern systems don't wait for events to happen. They simulate possible futures. Using physics-informed neural networks, AI models estimate trajectories based on acceleration, drag, and environmental constraints. For example, if an object's velocity is v and acceleration is a, its future position xt is estimated using. These equations run continuously inside prediction modules, updating hundreds of times per second. The system essentially lives slightly ahead of reality. This predictive ability is what creates the illusion of superhuman reflexes. Now add machine learning. AI models are trained on millions of examples. They learn statistical patterns that humans would never consciously notice: micromovements, shape asymmetries, thermal gradients, pixel correlations. This learned intuition allows machines to recognize situations after seeing only partial information. Humans require context. Machines require data. This is why AI can identify objects partially hidden by fog, shadows, or motion blur. The next layer is attention modeling. Transformer-based architectures dynamically focus computational resources on regions of interest. Instead of scanning the entire image uniformly, attention mechanisms zoom into areas showing unusual motion or contrast. This reduces processing load and accelerates detection. It's machine curiosity, mathematically implemented. Now let's zoom out. Why does this matter scientifically? Because we are witnessing the emergence of artificial perception systems that rival biological senses in speed and exceed them in consistency. Machines do not tire. They do not blink. They do not lose focus. Their reaction time does not degrade after hours of operation. This capability is not limited to defense or robotics. The same perception stack powers self-driving cars, medical imaging, factory automation, wildlife monitoring, and disaster response. AI detects tumors in MRI scans faster than radiologists. It identifies cracks in bridges invisible to the human eye. It tracks endangered animals through forest canopies using thermal imaging. The physics is the same. Photon A circumflex, electron A circumflex, tensor A circumflex probability. That's the entire chain. Future systems will go even further. Neuromorphic chips already mimic biological neurons using analog circuits. These chips operate asynchronously, consuming microwatts of power while processing events in microseconds. Event-based cameras only transmit changes in brightness, eliminating redundant data and achieving reaction times below 1 millisecond. Quantum-enhanced sensors may soon detect single photons with near-perfect efficiency. Optical neural networks process information at light speed. Edge AI systems will embed perception directly into sensors, removing transmission delays entirely. Eventually, perception will occur at the hardware level. No frames, no buffering, just continuous awareness. But the most profound implication isn't speed, it's scale. Billions of machines are gaining perception simultaneously. Cameras, drones, satellites, vehicles, factories, medical devices, all becoming intelligent observers. Humanity is building a planetary sensory network. Earth itself is acquiring eyes. This raises enormous ethical questions, but also unprecedented scientific opportunity. Climate monitoring, disease tracking, ecological preservation, infrastructure safety all depend on fast, accurate perception. We are transitioning from reactive systems to predictive systems, from observation to anticipation, and it's happening faster than most people realize. AI doesn't lock onto targets. It locks onto patterns. It doesn't see objects. It sees probability fields. It doesn't react. It predicts. That is the true revolution. Curiosity ending retention loop. If machines can perceive reality faster than we can, if they can predict motion before it happens, and if perception itself becomes embedded into the physical world, then the next question becomes inevitable. What happens when reality is being interpreted by artificial minds everywhere at once? CDA Series Optimize. Subscribe for the next episode, where we explore how AI predicts the future using physics-based neural networks, because the future of intelligence isn't artificial anymore. It's everywhere.